Так, наш доклад посвящен технологии изготовления и исследованию белых фосфорных материалов, основанных на карбонизированных нанокомпозитах. Список участников приведен, и я начну доклад. В настоящее время использование иллюминофоров, особенно в сочетании со светодиодами, находит широкое применение в современных технологиях при создании дисплеев, мобильных устройств, подсветки экранов,
displays, screens, TVs, monitors, intellectual systems of residential areas, streets, using car lights, indicators, all kinds of colored markers in biology and medicine. White phosphorus are such materials that can absorb high energy shortwave signals from crystals and convert them into a wide spectrum of gamma colors or in other sources of light. According to the prediction of French company Yellow Development, that makes marketing research and research in strategic consulting and finance, in the next 5 years, the market of white phosphorus will grow and reach the point of $1 billion. In September, the study of market and technological patent, the company reached a conclusion that intellectual product connected to white light phosphorus remains the main driver of the market of LEDs. One of the main arguments in favor of such conclusion is the fact that today the patent for white phosphorus materials is 44% of the general amount of patents in this field. Nowadays, the main interest in LED lighting is white phosphorus that are able to generate warm white light that should maximally correspond to solar light index that goes through Earth's atmosphere. The problems of white light are solved with white phosphorus, cerium, europium, or terbium. These white phosphorus are used as coatings of blue LEDs, LED chips, the so-called contact technology, or the mixture of phosphorus with transparent polymers, such as polycarbide, based on which a light-transforming element is created with complex geometry, remote from the source of light. This technology of remote phosphorus, which is widely spread today. The mixture of white phosphorus contains the band of green, white, and red. Here you can see them on the table, and this allows us to convert the blue light that the LED produces into white light. The chip from one phosphorus has a lower index of light, which limits its application for lighting and is rather harmful for human sight. But as we can see, all the white phosphorus have these chemical elements. These rare earth elements are basically rare, and if we use them exclusively, production cannot be on a massive scale. And most of the rare earth elements are located in China. Only 5 or 6 companies that, here you can see them on the top of the slide, the Japanese, the Chinese, American and Korean companies, they basically dominate on the white phosphorus market and retain high prices. Therefore, many new companies are sprouting. They are trying to research and apply the new types of white phosphorus. Here you can see them on the bottom of the slide. Molybdates, tungsten-based, and other. One of the most promising is quantum points, or quantum dots, but they use heavy metals in their production cycle. And as we can see, the activators, as activators, still rare earth elements are used in these elements. Goal of our project, therefore, was to develop the new cheap technologies and the new type of white light producing materials without rare earth elements based on nanostructured silicon oxide. The research activity was focused on studying the mechanisms of emitting the white light by such composites. Let us dwell on the description of two technological processes of obtaining such materials based on the silicon oxide as a silicon base and the powder. To produce the layer, we use the following technological process. The basis, the monocrystal silicon, by using thermal treatment, we have 4-micron layer. Then it's treated by ultraviolet, which produces white band of visible light, which is typical for layered silicon. Next stage, the layers of porous silicon were thermally treated by a gaseous mixture as nitrix temperature of 1000 degrees for several minutes. As a result of this treatment, based on the microscopy, electron microscopy, the condensed dispersion of light, we can see porous silicon, and the red band disappears. Then there was thermal treatment, 650 degrees Celsius, and as a result we form a special material, carbonized porous silicon oxide, which when treated by ultraviolet laser light emits the white light, which is close to a natural sunlight. Our studies showed that carbonized silicon oxide, the blue band, the blue component of the whole band, of luminescence connected to light emission with a defected part of silicon oxide is determined by carbon, whereas the spectral properties of the band of photoluminescence can be regulated by thermal treatment of carbonization. We assume that this is due to change of the size of carbon nanoclusters due to temperature treatment. With the decrease of the temperature of carbonization, the size of nanoclusters decreases, which leads to the energy, the shift of carbon band to the short wave band. But these technological processes have a lack of control over homogeneousness of porous silicon, and not enough of control over matrix of creating such a layer. The nanoclustered carbon for silicon oxide matrix, we developed a new method of synthesis of white luminophore, which allows us to better control the silicon oxide matrix, and as a result, to obtain photoluminescent material with very well reproduced properties. We know that the Institute of Chemistry of Surface has been busy obtaining fumed silica and sorbents. We suggested a joint work using the nanodispersed silica, and through chemical treatment of these powders with thermolysis. The following operation, the powder was synthesized by high-temperature hydrolysis of porous silicon in oxygen-hydrogen flame, 10 to 12 nanometers thick of a particle. On the surface of these particles, there's a selenous group that give the hydrophilic nature to the silica and can participate in various reactions with organic compounds. Followed by chemical modification of the surface and building compounds with a certain number of position of atoms of carbon on the surface of silicon oxide with use of radicals, which are used for chemical modification of the surface of silica, phenolsilane, and the, as strange as it may sound, the cane sugar or sugar, saccharobiosa. Phenol silica, after drying, is treated thermally at a temperature of 700 Celsius during 30 minutes. At high temperature, the hydrogen is emitted, and hydrogen groups, and the carbon is produced as part of this operation. The nanopowder emits intense white light when treated with ultraviolet or violet light, which in its properties is close to the properties of solar white light. As our studies showed, with other chemical treatment of silica precursors with further thermal treatment, the main role of the carbons is to be the source of two competing processes. There's a forming of light-emitting nanoclusters of carbon and the growth of graphite-like compounds. The optimal temperature for thermal treatment for luminescence depends on the number of atoms of carbon per radical and the number of radicals per one nanoparticle in silicon oxide. We have shown that the maximum intensiveness of the band of photoluminescence can be shifted by adjusting the temperature of thermal treatment. With the decreased temperature, so by regulating the temperature, we regulate the size of nanoclusters, nanoparticles. With the decrease of temperature of carbonization, the size of nanoclusters decreases as well, which leads to the change in the energy of nanostructures and the shift of the band toward short waves. This correlation allows us to vary the luminescence of our powders by adjusting the temperature and also to tune into different hue of the light. I'd like to remind you that in 2012, the standard for office lighting is 70. We have the index of color rendering about 90, and the calculation in the light diagram here on the slide, our light of our powders is within the white zone in the graph. The comparison of our spectral properties of photoluminescence with a black body indeed shows that 90% our samples match, and on this slide we can see our correlation, and the correlation of our powders and the usual commercially available lamps, luminescent lamps. We see that our spectral properties are way better than the white phosphorus that is used in the readily available lamps. Unfortunately, we only have one disadvantage, that the efficiency of the lighting is about 35%. 35% of the efficiency of the commercially available white phosphorus. So if we were to conclude shortly, what are the advantages of our technology? We don't need rare earth elements or heavy metals and the full environmental safety. The broadband photoluminescence, which covers all the bands, the maximum photoluminescence is within the band of 550 nanometers, which matches the retina of the eye, and the ability to vary the light properties without the change of white phosphor itself, to vary the spectrum of white light. Our material is cheap, and as precursors we use sugar, and affordability and availability of the materials. We use silica, we use oxygen, and we use carbon. That's it. The technological process does not require any huge investments, and it's environmentally safe. We obtained 2 patents this year for our white phosphorus. And I'd like to say the following, that the technological process, although it's still in its pilot stage, but it is easily converted into for industry production scale. So, because everything, all the the technological processes with silicon dioxide or silicon are available. These are the recent publications, and this work was supported by UNTC, by the President of the Academy of Sciences, and I think we should be really thankful for that. Thank you. Енергоефективність переводу електрики в світло. We did not study electric luminescence, we studied photoluminescence. But electroluminescence, we looked at it briefly. But the same, we could produce white light. We can have in the same device white light, green or red light. So what's the efficiency in percentage? Yeah, I cannot tell you that. Let me explain. The efficiency, this is the way we measured efficiency. We took white phosphorus from a commercially available lamp produced by Philips. We measured the bandwidth, and we measured our bandwidth, and we compared our powders, the spectral properties, and the amplitude. As I said, 30%, we obtained 30%. Okay, thank you.
Thank you once more.